Okay, so how do we tackle difference equations using the Z transform? So I'll just work through an example. The key here is applying this property that we just covered in the previous video. Work through problem 5.3-3 in the text, where we're given this difference equation: 2y of n plus 2 minus 3y of n plus 1 plus y of n is equal to 4x of n plus 2 minus 3x of n plus 1, and I'm given the initial conditions. Y of minus 1 is equal to 0, and initial conditions for difference equations are, instead of derivatives, which we don't have for discrete time signals, the initial conditions for a second order system are typically given at y of minus 1 and y of minus 2. For a third order system, with a third order delay here, you get an initial condition on y of minus 3 as well. And we're interested in finding the response of this system for this input. X of n is 4 to the minus n times u of n, and we want to find the output. First step is here, since our initial conditions are for n less than 0, we want to use the delay form of the difference equation. So the largest advance here is 2, so I'm going to substitute in n minus 2 for n everywhere, and I will get 2y of n minus 3y of n minus 1 plus y of n minus 2 is equal to 4x of n minus 3x of n minus 1. Okay. And then now I'm going to split this into two parts. I'm going to actually find, let me actually get a new board here. We'll find the zero input component, the zero input response, also known as the free response, and find this by actually setting the right hand side of my difference equation to 0. So I'm going to put little subscript zeros on my y here to indicate that this is just a component of the total response. So rewriting the difference equation I just had, but with the input set to 0. Now I can take the Z transform. Because the Z transform of y0 of n is just y0 of z, and then for this term I'll have 1 over z y0 of z plus y of minus 1, is my initial condition appearing, plus 1 over z squared times y0 of z plus 1 over z y of minus 1 plus y of minus 2, all equal to 0. So I'm going to factor out the y0 of z term wherever it appears, and so I'll have 2 minus 3 1 over z plus 1 over z squared, all times y0 of z, and then writing out my other terms, I've got a minus 3 y to the minus 1 plus 1 over z y to the minus 1 plus y of minus 2, all equal to 0. Now I can plug in my given initial conditions. Y of minus 1 is 0, so these two terms go away. Y of minus 2 is equal to 1, so this simplifies to z squared y0z. This is equal to 1 when I take it to the other side by subtracting it from both sides. It's equal to minus 1. So now I can find y0z is equal to minus 1 over 2 minus 3, 1 over z plus 1 over z squared, and multiplying through by z squared to get this in a ratio of polynomials in z. 2z squared minus 3z plus 1 in the denominator. Writing this now in standard form with the coefficient of the leading term being 1 in the denominator, z squared over z squared minus 3 halves z plus a half. Now we want to go through and find the inverse z transform of this. Actually, this has, take one more step here. This actually has, the denominator has real roots at 1/2 and at 1. So I can do a partial fraction expansion now of this. I do a partial fraction expansion actually of y0 over z, remember, and then work through and find the inverse z transform. I'll leave that to you as an exercise, but going through that we get y0 of n, the zero input response, or the free response, is 1/2 to the n minus 1 all times u of n. Okay. I can plug the initial conditions in here again, ignoring the u of n part, to see that this equation actually does satisfy my initial conditions. Now let's turn to the other component of the response, the zero state response, and here I'll use the subscript x to indicate that this is the portion of the response due to the input, and just rewriting my difference equation, and minus 2 here is equal to 4x of n minus 3x of n minus 1. I want to take the z transform of this, but in this component all my initial conditions are 0, so this just becomes 2y of x. I'm going to leave off the parenthesis z notation, minus 3, 1 over z, y of x, plus 1 over z squared because of the delay by 2. Again, leaving off the initial conditions, they're all 0 in this part of the problem because we handled those previously. This becomes 4, the z transform of x, minus 3 times 1 over z times the z transform of x. So factoring out the y of x, I'll have 2 minus 3 times 1 over z plus 1 over z squared. Y of x is, and then factoring out the x, 4 minus 3, 1 over z x. I'm going to go ahead and multiply by z squared here. So I'll have 2z squared minus 3z plus 1 y of x is equal to 4z squared minus 3z x. And now I can find the ratio of y of x to x. That's our transfer function, which we call h of z. In this particular case, it's going to be 4 z squared minus 3z over 2z squared minus 3z plus 1, or I can rewrite this as 2z times z minus 3, factored the 4 out of the numerator and the 2 out of the denominator. So I'm left in the denominator with z squared minus 3 halves z plus 1. This is the same denominator that we had for the free response. So now, in order to find the forced response, I need to actually take my transfer function and multiply that by the z transform of my input. And for the given input I had, x of n is 4 to the minus n u of n, x of z is z over z minus 1/4, not a half, 1/4. And so now I can get yx of z is the product of these two, h of z times the z transform of my input. So writing that out, I'm going to have z squared 2z minus 3 halves z minus 1/4, and then factoring that second order polynomial z minus 1/2 times z minus 1 as we did previously. Then now do a partial fraction expansion again of y of x over z, and then take the inverse z transform of those terms. That leads to yx of n is minus 4/3 1/4 n plus 2 1/2 of n plus 4/3 all times u of n. So now I can put the two pieces together to get the complete response. It's the sum of the free response and the forced response, or the zero input and zero state responses. So y of n is the y0 component plus the yx component. And putting all those pieces together and doing a little algebra, I get, as a result for this problem, the output is minus 4/3 1/4 n plus 5/2 1/2 n plus 1/3 u of n. Had to do a lot of algebraic work to get this result. It would be nice to have some way to verify it. I'll actually show you in a project how we can use MATLAB or Octave to find the response of a discrete time system for a given input. And so we can use Octave to actually find the response of this system in this example for this input, or solve this difference equation. And then we could compare our theoretical result to the result as calculated by Octave, to hopefully give us some verification that our theoretical solution is correct. And it's pretty easy to do in Octave to generate this output. So we'll do that in our next project.